we are going to start a new topic. So, this is we are going to start talking about the translation and rotation of rigid bodies. So, so far in this course the examples that we have discussed were mostly almost all the examples were, in some cases we took point masses, in some cases we took extended objects, but in most of the cases we are talking about translational motion of the object of our system. Now, we are going to focus on the rotational motion. Now, in addition, we are now going to look at extended objects, the objects which are no longer a point mass, but a mass distribution which is distributed in space over certain region. Now, the rotational motion has a few counterintuitive concepts that are slightly different from the translational motion. So, I am going to emphasize on discuss two such things. So, let us first point out one very key difference between the rotational motion and translational motion. Now, we know that if we take if we look at the displacement of an object, translational motion, let us say I can go along any path. So, for example, I can go from here to there along let us say this is along x direction, this is along y direction. I can go first along x direction and then take in the y direction, let us say in the y direction, or I can first go along y direction and then take the x direction. So, we both in either way, either route we reach at the same final position. This is no longer true for the case of rotation. For example, suppose I take an object like this and let us say this is my x axis and this is my y axis, and I want to rotate this object along the x axis first and then y axis. So, then I rotate along x axis first and then y axis. So, this is now the orientation of this particular object. Now, if I do the opposite, I want to rotate the first along y axis by an angle 90 degree, same angle 90 degree as which did in the previous case, and then along x axis by the angle 90 degree. Then I end up the object with a different orientation. So, look that this orientation is very different from the orientation we got earlier when we first rotate this object by an angle about x axis first by an angle 90 degree and then about y axis. So, this shows that finite rotation does not commute. Two finite rotation does not commute. So, there is no vector addition of two finite rotation. Finite rotation means rotating by about an axis by an finite angle. So, this is the first kind of difference from translation and rotation. So, this is kind of slightly counterintuitive. So, in rotation we can only talk about infinitesimal rotation which are kind of commute, and we can define vectors out of that. So, when we talk about rotation, so the key quantity is the not the displacement, but the rate of rotation. So, rotation by an infinitesimal amount. So, we are going to discuss it in detail later. So, here I would like to point out the learning objectives for this part of this module. So, first we are going to consider the extended object, and we want to define two key properties of the extended object that defines their mass distribution. So, the first property is the center of mass. So, how to find the center of mass position of an extended object, and the second property is about something called moment of inertia, which is the analog of mass, but something more complicated and but a fundamental quantity to describe rotational motion. Then we will sort of look at the basic concepts and laws that are required to describe rotational motion, and then we shall apply our systematic modeling approach to sort of analyze problems with rotational motion through several examples. First, let me give you some examples of extended objects. So here are like different examples which are at different dimensions. So this one is an object which is a line. So this is a mass distribution distributed over a line like a wire. So this is an example with a one dimensional mass distribution. Then this one is an example of a set of gear. So if you assume that these gears are very thin, then kind of if you ignore the thickness of the gear, then this becomes a planar object. So this mass distribution is planar. So this is an example of a two dimensional mass distribution. Now if you include the thickness of such gears, then you get a thin plate, and this is, we can sort of think of it as something like a pseudo two dimensional mass distribution. Finally, we can get a fully three dimensional object and a fully three dimensional mass distribution. Now, from engineering point of view, most of the engineering machines are kind of made up of different parts. So, this is an example of something called composite objects, which is made of different parts, and in those cases, so these are like in the practical cases which are most important from engineering point of view, is that this kind of composite objects which are made up of different parts. Now, if you look at these examples, so each of the examples we are talking about objects with very simple shapes, like this is a line, this is a circular mass distribution, this is a somewhat irregular mass distribution, this is a cubic mass distribution, and in this case this is a example of a composite object with a sphere, combination of spheres and lines. Now, an interesting consequence of having finite size and shape, which I would like to point out. So, if you look at around you, and if you look at, for example, you will find that these extended objects are broadly, there are two different varieties. So, the first one is what we call compact object. A compact object like this cat or this ball. So, in this case, so they more or less have let us say lot of objects which has more or less uniform density. So, the distribution of mass of that object and the distribution of volume of that object are kind of roughly proportional to each other. So, the mass is proportional to the volume. So, if you take a bigger cat, its mass will be bigger. So, if the volume of the cat goes by, increases by a factor of 2, so you expect the mass will also increase by a factor of 2. Now, there are another kind of objects, the most prominent example are the trees. So, these are, if you look at a tree such as this banyan tree in this picture, most of the mass is actually concentrated in the trunk, which occupies a small volume. Most of the volume is due to the surface area of the tree, and the surface area of the tree is enormously large because of the leaves. So, most of the surface area and the volume of the tree comes from the leaves, but the leaves has mass which are kind of very negligible compared to the trunks. So, in this case, so this is an example of a shape or distribution in which the volume distribution and mass distribution are separated. So, it is for the trees, it is no longer true that if you increase double the size of the volume, you can do double the size of the volume by increasing the number of leaves of the tree, but that is not going to add to the mass too much. On the other hand, you can double the mass by making the trunks thicker, but it is not going to add much volume to the tree. So, these kind of objects are called fractal objects. Now, there is a reason that if you look at animals, most of the animals follow these like a compact objects, and most of the trees follow this kind of like fractal objects. The reason being that animals are movable objects. So, so they need to conserve energy. So, they need to minimize the amount of energy they spend for movement, and so that is why they are more compact. On the other hand, trees want to maximize their surface area to catch sunlight. So, that is why they have evolved to become a fractal object. So, this is a side note. So, now our basic goal of so we will start our discussion by looking at these two properties of how to characterize this mass distribution, and the first property is the center of mass. So, center of mass, as you all know, so I am sure that you have studied center of mass in your high school. So, if you have a collection of point mass, then its center of, and each point mass has a mass mi and is located in space as a, let us say this is a collection of point mass like this is a, and let us say with respect to some arbitrary origin, the location of this point is r I. Then the center of mass is given by the weighted sum of some weighted mass weighted by its location. So, this numerator is a vector mi times ri, r is a vector. So, it is represented as a bolt, and such that and divided by the total mass of the system of point particles. So, that gives you the location of the center of mass. Now, and if the instead of point particles, if you have a more continuous mass distribution, then this sum will be replaced by this integral. So, you have a small element of mass dm at located at some so this is a location of the this dm with respect to, this is my origin. So, this is x, this is y, and then let us say you have a object which kind of a square, and this is one element of the square. Then the total mass or center of mass of the square will be given by the element times location integral over all the square divided by the total mass of the square. Now, so this is the mathematical definition. So, the question is that why do we need center of mass? So, take the example of a ball. So, I am sure that all of you have seen some cricket match where a bowler delivers a ball. So, the ball is an extended object. Why? Because the ball is a projectile. If you consider this ball as a projectile, then a point mass, a projectile is a point mass, then if you ignore all the forces except gravity, then you expect that it follows a parabolic trajectory. If you include the effect of the drag force due to the air, drift force etc. due to airs, you may explain that the trajectory can deviate from the parabola, so that the ball can swing. But the ball also spins about its own object own axis. So, that motion is also crucial for the particular delivery, and in order to explain that, you must assume that the ball is an extended object, the cricket ball. But now, when the ball is moving, so it is it is spinning and moving. So, it is rotating about its own axis and it is moving in space. So, it follows actually each point of the ball. If you track each point, one point, let us say you put a dust particle on the surface of the ball, and if you look at the trajectory of the dust particle as it moves through the air, it is a complicated trajectory, but on the whole something in the ball is still moving in a simple almost parabola like trajectory. So, this something, so this is the representative point of that sort of represents the ball as a whole. So, this is the center of mass. So, you need that. So, to a mass distribution, something that is extended in space, to a first approximation, you can replace it by a point mass to describe its properties. And then you have to the question will come that where you want to put this point mass, location of the point mass, and that location is given by the center of mass position. And as you know that when we consider the gravitational force, so the gravitational force will act on each and every element of an object, but if you look at the total force on the full object, so that will still act through the center of mass. Now, in this case we are going to consider a problem of the following type. So, we are basically going to the problem that we are going to discuss is given an object that if you given the shape of an object, then find the center of mass position. And in this case we shall see that the essential problem, mathematical problem, is to how to describe a single. So, we are going to do it in two steps. So, we are going to describe a single mass element dm, and then we do this integral to calculate the center of mass. So, here are few examples of objects of simple shape. So, let us take a circle. So, this is a ring, and in this case the mass is distributed on the perimeter. So, on the perimeter, so shown as this blue line along a circle. So, this is an example as before as a 1D mass distribution. Now, so these are kind of common examples for which it is relatively easy to compute the center of mass. So, we can take a full circle, or it could be a half circle, or it could be a quarter of a circle, or an arc of a circle, a part of a circle. And then if the 2D version is that if the circle is filled, instead of a ring, if we have a plate or a disc, so we can have a mass distributed throughout a filled circle, or a half circle, or a quarter circle, or a part of a slice of a circle. So, these are objects of simple shape in 1D and 2D for which we can calculate the center of mass relatively easily. Now, if you take a circle and then if you make a rotate it about in 3 dimensions in the third direction, then you get a 3D object of revolution. Now, when you go from 2D to 3D, let us say if you rotate a circle about any of its diameter, then you generate a solid sphere such as shown in this figure. Now, some variation of solid sphere can be a spherical shell, hollow empty spherical shell. So, the mass is concentrated only on a thin shell, but nothing is inside. The inside of the sphere is empty, or it could be a half sphere, hemisphere, or it could be a part of a sphere. The other way to generate a 3D object from a 2-dimensional circle is to consider the z axis, which is perpendicular. So, this is x, this is y, and this is z, which is perpendicular to the screen, and then translate this circle along this z axis. Then what you generate is a solid cylinder, and again there could be variations of this kind of object, which could be a hollow cylindrical shell, or a part of a cylinder, a cut cylinder, or a part of a cylinder. So, these are like objects, there are various common objects that are kind of useful to describe different practical engineering machines. Now, another example is that a triangle. So, another common shape in 2D is a triangle. So, you can take a mass which is distributed in a filled triangle or a part of a triangle in 2D, and then what will be the center of mass location, and then from the triangle you can generate a 3-dimensional object of revolution, which is a cone, or it could be a conical shell or part of a cone or cone, etc. So, these are the various kinds of common shapes for which the problem is to find, given these objects of different shapes, of these are some examples of the shapes, and find the center of mass. Now, I will take an example to sort of give you like how to find out the center of mass. So, consider that a thin hemispherical shell. So, this is a hemisphere of radius r, and this is a shell. So, the inside is empty. So, the mass is distributed over the surface of the shell. So, what is the center of mass location? Now, by symmetry we can see that the x, so if this is my x axis and this is my y axis, by symmetry we can see that the if we assume that the mass distribution is uniform, then the center of mass must locate along the y axis. So, the question is that what will be the height, at what height from this x z plane, the equatorial plane of the sphere will be the center of mass. So, for that let us consider, so a ring as shown here. So, this ring is makes an angle theta with the x axis. So, this is the elevation of the ring, and it has an area which is given by the length times width. So, the ring perimeter is this length, which is 2 pi r cos theta, because the radius of this ring is r cos theta, and then the width of the ring is this arc length, and this arc length is given by r times d theta. So, the area element of this mass, this strip of ring, the mass will be sigma. So, sigma is the density. So, the mass per unit area is, so we are going to assume this is constant, so it is uniform. So, this is given by this particular expression, and then the, by definition, the y location of the center of mass coordinate is given by the y times dm. So, the location of any y coordinate of any point of this ring, that is the elevation of this ring, is given by r sin theta, which is clear from the picture. So, this is y and this is dm, which is given by 2 pi r square sigma cos theta d theta. So, and then the total mass m. So, we can sort of calculate easily that the, if we take a sphere, then the total surface area of the sphere is 4 pi r square and times sigma, that should be the total total mass for a sphere. But we have a hemispherical shell, so the surface area, and so this equatorial plane is empty, this is our assumption. So, this is the surface area of a hemispherical shell with empty equatorial plane. So, this is m. So, this is m. So, this factor, the integral, and then this is at a particular length theta. So, then if we sort of move this ring up and down from all to cover all possible values of theta, then we have to integrate it from 0 to pi by 2, which covers all possible values of theta. So, after simplification, so we see that this integral is given by, so m is 2 pi r square sigma. So, what we have on the numerator is 2 pi r cube times 0 to pi by 2 sin theta cos theta d theta and times sigma, and in the numerator you have 2 pi r square sigma. Now, this integral, so let us call that I. So, this you can see that this is sin theta times d of sin theta, because 0 to pi by 2, because d of sin theta. So, if you put sin theta equal to x, then this is just x dx. So, this is half sin square theta, and x theta equal to 0, sin theta is 0, theta equal to pi by 2, sin theta is 1, goes from, so this is just half. So, what we get is, so this after calculating cancellation we only r remains. So, this r times half. So, you get this location to be at the middle. So, this is probably something we can guess by symmetry. So, the location of the center of mass will be of a hemispherical sphere will be at the middle along the y axis. So, we shall consider more interesting examples of center of mass in the next lecture. Thank you.